Okay, Anne, I think, has gone off the line. So our speaker today is Bob Mackenzie, known by one and all, and he's going to give us a talk on weather today. Bob, take it away.
Okay. Oops, already hit the wrong button. So the big picture, the first one is this title should really be climate. Climate is what you're supposed to get. Weather is what you actually get. And it's much more complicated than what I'm going to explain, but I hope there's no meteorologists on here. Basically, there's four major concepts. And if you can take away with these four big ideas, you've been successful and I've been successful. So I'm going to start with the first one. I'm going to use the first thing that we do is we look at the world. This is the equator. If you can see my mouse here, Norm did a great job on the mouse. At 30 degrees north latitude, the equator is 0. This is the first third of the Earth. And if you'll notice the 30-degree latitude line, there's a desert in the United States. There's a desert in Africa. There's a desert in Asia. In the 30 degrees south latitude, there's a desert all the way across. Now, I'll do this in more detail, but the important thing to remember here is the reason that I'm mentioning this is where we live. We live at 34 degrees north latitude, and so we live in a desert. So the big picture here is, number one, you've got to realize that our basic climate is a desert climate. So take away that one. Second thing is the worldwide wind patterns. Again, this is the equator along the bottom here. This is 30 degrees north latitude. And you'll notice that in the tropic third of the world, the winds blow towards the southwest. So the Spanish would ride these winds all the way across the Pacific Ocean. We live just north of this 30-degree line. In this area, which is called the temperate third of the Earth, the winds blow from the southwest to the northeast. And so the prevailing wind in our area is from the southwest towards the northeast. So we live in a desert and the prevailing wind is from the southwest blowing to the southeast. That's the second major macro thing you should learn about the weather, hopefully. The third one is all of the oceans have what's called gyres on them. Our ocean is the North Pacific Ocean, and the gyre is a clockwise rotation of wind and current that covers the entire ocean basin. All of these oceans have gyres. So the North Pacific has one, the North Atlantic has one, and you'll notice it's going clockwise. In the Southern Hemisphere, the South Pacific goes counterclockwise. So everything I say about the Northern Hemisphere has a mirror image opposite in the Southern Hemisphere. The Indian Ocean gyre, again, is counterclockwise. The South Atlantic gyre is counterclockwise. There's also a gyre up in the North Pole called the Beaufort gyre, and this has become very, very important as the Arctic warms and the ice is melting. It's a big factor in the ice melting. There's also a gyre in the South Atlantic. It's got all kinds of names from the sailors. Finally, the jet stream. The jet stream is like a hose. It's very thin. It's only a few miles in diameter. It runs from west to east very fast, 200 miles an hour. And this has a profound effect on our weather, a profound effect. Now, just quickly reviewing, the deserts are caused by Hadley cells. The gyres are caused by Hadley cells and Coriolis effect. The jet stream is caused by Hadley cells. And so an important thing we need to look at is Hadley cells. The land breeze, sea breeze is a local feature, and that'll be in the next video, but that's the major local feature that we have on our Palos Verdes. All right, a couple of quick things. If you put air under pressure, like in a bicycle pump, it heats up. This is important because we live in an area of high pressure air, which is hot, and that contributes a lot to our desert climate. Second, if you have equal volumes at equal pressure, hot air is less dense than cold air. See, it's because the air molecules have much more energy and they need more space. Now, there's two things that come out of that. The hot air is light, and so it will rise up. Cold air sinks. So hot air rises, cold air sinks. Another thing is counterintuitive is that since there's a lot of space here with less molecules, other things that don't interfere can get in. And the major one is water in its vapor or gaseous state, water vapor. So hot air can contain much more water vapor than cold air. We call this hot air vapor humidity. And this is going to be important. Lastly, the Earth wants to equalize everything. So air molecules run from high pressure to low pressure. And that flow of molecules is called wind. So wind blows from high pressure to low pressure. That's the end of our physics lesson. Hot air balloons rise because they have hot air in them. Hot air is less dense, fewer molecules. And so balloons rise up, just like a wood, which is less dense than water, floats up to the top of water. The balloons are doing the same thing. They're floating on heavier air. All right. The most important concept from meteorology is something called Hadley cells. If you understand this, you can understand most of what weather is all about. So if you go to the equator, and this is the equator right here, the first thing you're going to notice when you get off the plane is the air feels thick and heavy and sticky. And this is humidity in the air. And what it is it's water saturated in air. Hot air can contain more water than cold air. And so whenever you go to the tropics, you always think of humid, sticky air and hot. And it's hot because the equator on average is the closest point to the sun on the Earth. The other thing you'll notice in the tropics are famous for their puffy white clouds. There's a reason for all of this. So what happens is if you're at the equator, this hot air is going to rise. Hot air rises, and so it will rise. And all sorts of things happen when that air rises. The first thing it will do is it creates a relative vacuum. As the molecules go up, there's nothing here. And so this tends to suck the higher pressure air from the North Pole to the equator. So the air from the North Pole wants to flow across the face of the Earth and go to the equator. Same thing with the South Pole. As this air rises, it begins to cool off. And as it cools off, it loses its capacity to contain water. The humidity goes down. And so what happens is that water that was saturated in the air is squeezed out in the form of water droplets. We call that a cloud. If we get enough of them, we call it rain. And so as this air rises up from the equator, it becomes colder and colder and drier and drier. Eventually, it hits the stratosphere, which is the second layer above the Earth. And all of this weather is taking place in an area called the troposphere. So when this troposphere air hits the stratosphere, it's got nowhere to go. The stratosphere is like a lid. And so the air flattens out and starts moving, some north, some south. We're going to talk about the north air. So the wind that's going north, which is now cold and dry, wants to go to the North Pole. Unfortunately, it's cold. Cold air is dense and it sinks down. It begins to sink down. It hits the Earth, in theory, at the North Pole and flattens out against the Earth and then comes back towards this relative vacuum and forms what's called a Hadley cell. So if you look here, you can see that there is a circular type of motion right here. This is called a Hadley cell. This is the theory. In theory, there's no difference between theory and practice. However, in practice, there is a difference. And so what really happens is there's a three-cell situation on the Earth. So this is the equator. It's very hot at the equator. The hot air rises, creating a vacuum of low pressure. It sheds its water, gets cold, hits the stratosphere, goes north, and doesn't make it. It only gets about a third of the way. And so now it sinks back down to Earth at 30 degrees north latitude. This is important because this is where we live. And it flattens out against the Earth and then flows south back to the equator and forms this Hadley cell here. Some of the air that hits the Earth when it descends goes north and into the temperate zone. And it hits it hits the cold polar air that's coming down from the North Pole. And so it's pushed up and forms another type of Hadley cell called a Ferrel cell. So what we have here is like we call an egg beater. So it comes up and around, back down, up, around the ferrule cell, back down again, comes back around, goes back up to the North Pole here, comes around, comes back over the ferrule cell, comes back down, hits the Earth, goes to the Hadley cell. So this is the general circulation pattern of the Earth. It's much more complicated than this, but this is the basic idea. And you see where the air is rising at 60 degrees, it's shedding its water, and where it's rising at the equator, it's also shedding its water. The air at 30 degrees is very dry. It's dry. It doesn't shed water. This is a three-dimensional picture. Again, this is the equator, and this is the Hadley cell. You can see the cell rotating right here. So the Hadley cell is actually like an inner tube going around the Earth. So if you can follow this tube, a piece of it's been cut out. Here's the tube on the other side. So you can picture this as a three-dimensional inner tube all the way around the Earth. And there's three of those in the Northern Hemisphere. There's one here. This is the ferrule cell, and then there's a polar cell up here. So the Earth is surrounded by these three circulation cells. And this is the Hadley cell. Deserts. Okay. To give a little bit of theory here, this is the equator again. I'm going to ignore the Southern Hemisphere. So the air rises, sheds its water, the water is squeezed out, it becomes cold, it wants to go to the North Pole, doesn't make it, sinks down here at 30 degrees north latitude. Now remember, this air started out hot, it cooled off, it shed its water. So this air up here near the stratosphere is dry and cold. As it sinks down to the Earth, it's like a bicycle pump. It starts piling on top of itself, creating high pressure. That's what this H represents. High pressure, again, as I mentioned, causes heat. So this air here is hot and dry. The opposite of what this air is at the equator. This is hot and wet or humid. This is hot and dry. Now, we live right here. This is 30 degrees north latitude. We live at 34 degrees north latitude. So we're right here. So we're in this band of hot, dry air. When you think of hot and humid, you think of tropics. You think of Hawaii, Tahiti. When you think of hot and dry, you think of deserts. And that's exactly what we have here. This is hot and dry air caused by the descending air from these Hadley cells. And that's what causes the desert. What's important is this is where we live. So this is a macro climate as far as we're concerned. Again, notice that the deserts are all on this 30 degree north latitude where the cells meet. Notice one other thing. We live here. Notice the desert is on the western side of the continent, but not on the eastern side. In South America, in the south 30 degrees latitude, we have the Atacama Desert. This is the driest desert, the driest place on the face of the earth. But there's no desert on the right side of the continent. In Africa, we have the Namibian Desert. And in Australia, we have the Australian Desert. Eurasia is kind of a weird duck. The Sahara Desert is on the west coast, but we also have the Mediterranean Sea. And there's a high pressure area right over the island of Crete. And that also contributes to the Arabian Desert here, with the Arabian Gulf, Red Sea, Persian Gulf here. And up here, the Gobi Desert is a little bit to the north because the Himalaya mountains are right here. And that causes, it throws off the 30 degree thing a little bit, but basically the same rule holds. What we want to take away from this is where we live, and the general climate, the general area is a desert. There's another picture of the desert. All right, Coriolis effect. This is caused by the rotation of the Earth. The math in here is horrendous. If you look at Coriolis effect in Wikipedia, you can see the kind of equations that Einstein works with. It's very difficult stuff. But there's a very simple rule to take away from this. The Coriolis effect always turns winds to the right in the northern hemisphere. So if you have a wind that wants to go north, it's going to turn to the right. If you have a wind that wants to go east, it's going to turn to the right. If you have a wind that's going south, this would be the right-hand side here. So the winds are always turned right under Coriolis effect. Why do we want to know this? Well, worldwide wind patterns. Again, here's the equator, and this is 30 degrees north. So this is the tropics. Now, if you look at the Hadley cell right here. This is, see the Hadley cell rotating right around here. You can see on the surface of the Earth, the winds are going south. So this wind wants to go from 30 degrees to 0. It wants to go south. The Coriolis effect turns it to the right. So the prevailing wind in the tropics is towards the southwest. Again, this is these are called the trade winds. This is 30 degrees north latitude, and we live right above this line. Now, if you notice the cell over here on the right, this is the Ferrel cell. The air is descending, but instead of going south, it goes north towards the North Pole. So in the temperate zone, the winds are going from the north. That is, it blows from 30 degrees to 60 degrees. And that's the ideal. But in practice, the Coriolis effect turns this wind to the right. And so where we live, the winds come from the southwest towards the northeast. Very simple proof of this is you simply stand out at the whale watch area in the interpretive center, face the wind, look at a compass, and you'll see that the wind is coming from the southwest. So our wind blows from the southwest to the northeast. Kind of an interesting little thing here. Everybody thinks that if you face out to the ocean, you're looking west. That's southwest, and the wind is from the southwest. So our prevailing wind is from that direction. And that's another major feature of our local weather. If you sail west from Palos Verdes, you go to Santa Barbara. That's very counterintuitive. If you look at a map, you'll see why. The coast is tilted a little bit. I won a lot of beers over this in yacht club bars because everybody thinks if you look straight out in the ocean, it's west. It's not, it's southwest. But again, the two major things are that the area that we live in at 30 degrees is a desert, and the winds are coming from the southwest. Why isn't Palos Verdes a desert? Well, we'll continue. A little bit of interesting stuff here. This is the equator. It's got a fancy name, as you can see. The wind is rising, remember, so you can't sail in winds that are rising. So if you were to sail down to the South Pacific, you'd have to cross this zone. The sailors call this the doldrums. So you got a nice trade wind here, you run into where there's no wind, and if you don't bring gas in an engine, you're going to spend a month trying to get through this. Up here at 30 degrees where we live, the Spanish would sail down and follow the trade winds across the ocean, but then they'd have to come up north and they'd have to cross this 30-degree line here where we are, just south of where we live. And they'd run out of wind and they'd get stuck. And if they ran out of water, they'd throw the horses overboard because the horses drank a lot of water. So the saying was, if you see a bunch of horses floating around, you know you're at 30 degrees north latitude. So these latitudes are called the horse latitudes. The gyres. Now, our gyre is the North Pacific gyre, and it's a general pattern of winds running clockwise, and the wind is bringing the current clockwise. Every ocean has a gyre. I want to point out something about the North Atlantic gyre. Notice it's very high, and this gives us some interesting weather over here, and if I get a chance, I'll explain about it if I have time. So the question is, what causes a gyre? Well, the gyre's center is normally around 30 degrees. And remember, this is high pressure air and hot. So if you're a molecule of high pressure air, you want to get out of Dodge. That's the rule, high pressure to low pressure. So you try to leave this high pressure area, but the Coriolis effect turns you to the right. There's another molecule trying to get out and it wants to escape, but the Coriolis effect turns it to the right. So what you're getting here is a slight turn to the right. This is a little better diagram. The high pressure in the middle of the ocean is caused by the descending air. As it descends, it hits the ocean, tries to get out of the high pressure, and the Coriolis turns it to the right. So this air starts to make what's called a gyre, and that's a counterclockwise rotation. So in general, if you have high pressure, the winds around it are clockwise. This doesn't form over land because of the mountains, the rivers, the forests, topography breaks it up. It tries to form a gyre, but there are really no gyres on land. There's two big exceptions. If we get a chance, I can talk about that. One is in India and the monsoons. But basically, the rule is that the oceans don't stop this. And so every ocean has a general clockwise rotation due again to the high pressure. So you can think of it as a desert in the ocean if you'd like. This is another picture of the Gyre. This H is where the high pressure is. This is what the sailors call a hole. At the very top of the very entrance in the high pressure zone here, the air is coming straight down, and you don't want to sail in here because you don't check out. There's no wind. This is also where the giant Pacific garbage patch is, because it's an area of extreme calm winds. And the rotation here is very slow, and everything tends to go in there. You can see the winds coming around here. One thing you've noticed, I'm already contradicting myself. The weather is very complicated. I've already told you the prevailing wind is southwest, and yet here we have wind coming down here from the north. So this complicates the weather pattern quite a bit. But this is what saves California. Notice Hawaii is right here. So the Spanish would sail down around here, follow the Gyre up, go to Asia, and then follow the Gyre around down the California coast and back to Mexico. They avoided the hole. They had too many bad experiences. A lot of Spanish expeditions were lost when they sailed into this hole. And so they sailed around Hawaii for 250 years and never saw it. So that's why they don't speak Spanish in Hawaii. Now let's have a little fun with the gyres here. This part of the Gyre is at the Southern Ocean, and the ocean is very hot. And it's also humid. So if you're here, you're in Tahiti, for example, Hawaii, just south of Hawaii, this is hot and humid and sticky. And the Gyre is carrying this hot, humid, sticky air up around the ocean. So if you're in Asia or Indonesia, you're going to get hot, sticky air. So this is the wrong side of the Gyre. Also, in the North Atlantic Gyre, this would be Florida and Georgia. So when you think of Florida and Georgia, you think of hot, sticky weather. And this is exactly why, because they're on the wrong side of the Gyre. This is the hot, sticky side of the Gyre. Also, if you live in Florida and you have a little hurricane over here, the Gyre is going to carry that hurricane right into your backyard. And so when you think of Florida and Georgia and the Gulf of Mexico, you think hurricanes, right? As the Gyre gets up to the north, it also cools off, just like the Hadley cell. And so this air along here is rather cold and also dry, because the rain has been falling all out of it over in Asia. And as it comes down to California, it's nice and cool. And this is what saves us right here, this wonderful cool air from the Gyre coming down from the north. Unfortunately, the Gyre doesn't go inland, like I said. It only goes in about as far as the Santa Monica Mountains or the High Sierra. And so if you live in Bakersfield, you don't have the Gyre. So Bakersfield is a desert, and Palos Verdes is just a wonderful place to live. And that's one of the major reasons, the prevailing westerly wind and the Gyre bringing this cool air down, which keeps us from being a desert like Bakersfield. So those are the major macro stuff in our weather. One more thing I'd like, let me see, times, yeah, we got time. The North Atlantic Gyre up here is a little higher. This is a very, very, very interesting area of the world, especially in terms of the weather. Especially in terms of the weather of the first half of the 20th century. This part of the Gyre here is called the Gulf Stream, and it's quite warm, and it stays warm all the way up around. This is what keeps Europe, at least the west coast of Europe, very warm. For example, Paris, which is right about here, is the same latitude as Toronto. And the weather in Paris is much different than the weather in Toronto. Unfortunately, this Gulf Stream doesn't warm that part of the American coast. It's offshore there. But you can think, what about the difference between Paris and Toronto? That's due to this Gyre called the Gulf Stream. If you look at Copenhagen in Denmark, Copenhagen is the same latitude as Juneau, Alaska. Now, Juneau, Alaska is getting this cold air from the Pacific Gyre, but it's getting the warm air from the North Atlantic Gyre. So Copenhagen is very mild as opposed to Juneau, which you know what Juneau's like. Interestingly enough, Copenhagen is also the same latitude as Moscow. Now, Moscow is inland and doesn't get the effect of the gyre. So just like Bakersfield is hot and doesn't get our benefit, Moscow doesn't get the benefit of the Gulf Stream gyre, and so it's freezing cold. It's inland. Again, this would make a great docent paper here. So there's just tons of stuff that's going on here, and unfortunately, that's an entire lecture on its own. This is the center of the North Pacific Gyre. I didn't take this picture, but I sailed through it. It's not solid. You can't walk on it. It's like a soup. But it's the most horrible mess you ever saw in your life. It's just nothing but literally garbage, paper bags, straws, even beds and mattresses. It's just got everything in here. I lied when I said I sailed through it. We had to motor, of course, because there was no wind. But it's bigger than Texas. And it's like the elephant in the bedroom. We don't know what to do with it. There's all kinds of plans. Nobody has a clue about what to do about this gyre. The North Atlantic also has one. It's called this. You might have heard of the Sargasso Sea. You might have heard that mentioned. This is the bottom of the garbage patch. So you can see the stuff hanging down here. It's like, you can see it's more like a soup here. Okay, the opposite of a gyre is a cyclone. The technical name of a gyre is an anticyclone. And cyclones are one name for a hurricane. You can also hear the word typhoon. The word hurricane comes from hurricane comes from an Arawak Indian word. The Arawak Indians were in the Bahamas when Columbus arrived. Their word for this was huracan. A cyclone comes from the Greek, which means turning. And the typhoon is, I've understood, is some Chinese word like tifong or something like that. But they all are the same thing. We call them hurricanes in the Western Hemisphere. They call them cyclones in the Southern Hemisphere. And in Asia, they're called typhoons. But we're all talking about the same thing. These are associated with low pressure. Remember, high pressure is warm, hot wind. Low pressure is sticky, dry stuff, and that's got a lot of energy. The water molecules in the humidity have tons of energy, and this is the engine of a hurricane. In a low pressure, the molecules of air want to get into the low pressure. So let me in, and they start heading towards the low pressure. Unfortunately, the Coriolis effect turns it to the right. Same thing, this molecule is trying to get in, and it's turned to the right. And so what you get is a basic counterclockwise rotation around a low pressure. So high pressure gyres rotate to the right. Low pressure hurricanes rotate counterclockwise to the left. This illustrates what we call the Eggbeater again. Here's a molecule trying to escape from the high pressure. It gets out, but the Coriolis effect turns it to the right. Now it's looking for low pressure. It finds it, and now it turns into the vortex here going counterclockwise. These molecules don't check out. It's like the roaches. They check in, but they don't check out. No movement from low pressure to high. So how does that work? Well, eventually the molecules start piling up in the low pressure, and the two pressures equalize and life is good. But this is the general wind flow around storms. Here's a picture of a hurricane. You can just see the air spiraling in towards that low pressure. Just says, I want in, this is a party, let me in, and here they come, spiraling in to the center. And so again, this is a beautiful picture example of counterclockwise winds spiraling into the hurricane. Again, what causes it? Low pressure at the center, winds trying to get in, Coriolis effect, turning the winds counterclockwise. Here's another great picture of a hurricane. You can see this air here just wants to get in really bad. I want to join this party. I want in. So they spiral in, spiral in. This is a good picture of the famous eye of the hurricane. Now, one of the things, it's very complicated, but one of the things that caused the eye is the fact that this is rotating counterclockwise very fast. If you've ever pulled the plug on your bathtub, you notice you get like a whirlpool. It's actually a void area of very, very, very low pressure. And so the constant spinning around here creates, the centrifugal force throws the clouds out. And so it creates an area where there's very few of our molecules. This is one of the reasons that caused the eye of the hurricane, because it's just spinning around very, very fast. This is the picture of the inside of a hurricane. You can see it spinning around, spinning around, spinning around. Another picture here, very complex. This would be a great docent paper. There's all kinds of stuff going on in here, but you can see the general counterclockwise rotation, except at the top, interestingly enough. Tornadoes. Okay, the difference between a hurricane and a tornado is that hurricanes form over the water, and they're huge. They're hundreds and hundreds of miles wide. Tornadoes are very local. So this funnel here is not very big. It's not like 100 miles wide. It might only be a few hundred yards. And this funnel is the same thing. It's counterclockwise rotation going up. This line across here is called the shear. And hurricanes hate shear, tornadoes love shear. So tornadoes are formed over land, and hurricanes are formed over water. Hurricanes are very large, and tornadoes are very small, but they're both cyclones rotating counterclockwise. You can see in this side here that the air is rotating counterclockwise in this funnel here. You see the water molecules are turning up and around here. This is the eye of the tornado, by the way. Again, here's another picture of a tornado. Again, it's low pressure is causing that. Jet stream. Okay, now we come back to our friends, the Hadley cells. And there's a little bit of myth about jet streams, so let's talk about that. The Hadley cell is caused by the hot air rising. The water is being squeezed out, so it's dry, and it's descending. And the Ferrel cell, the air is being pushed north, coming up around here. So this round circle right here, this vortex, this is the jet stream. So at the top of the meeting of the two cells is always a jet stream. And at the bottom, we get either a desert in our case or the tropics at the equator. But the main thing you want to know about the jet stream is it's not the jet stream so much. It's the fact that it's the border. It marks the border between the two cells. So here we have the tropic cell, the Hadley cell, and the temperate zone cell. And it marks the meeting of the two, the wall. And air masses don't mix. So this air mass will not mix with this air mass. So the Ferrel cell air mass will stay separate than the Hadley cell. Similarly, the Ferrel cell air will stay separate from the polar cell. You can see here that the hotter Ferrel cell air is rising up above the polar cell, which is pushing below it, and they don't mix. Now, this is nice because this jet stream here is kind of like the guardian between the two air masses. And as long as it's behaving itself, the two masses are separate, which is important. There is a equatorial cell jet stream, which is not shown here. It doesn't really bother us. The subtropical jet stream is at 30 degrees north. If it behaves itself, it stays south of us in Mexico. When we get an El Nino, it doesn't behave itself. The polar jet is the one we normally hear about. It's at 60 degrees north latitude. This is in Canada. So if the polar cell is behaving itself, all of this action over here is taking place in Canada, and the temperate zone is living high on the hog. There's another sort of jet stream up over the North Pole called the polar vortex. And as the Arctic is warming, this polar vortex is becoming very, very important. You'll be hearing it more and more and more in the news. And this winter is a beautiful example of that. So it couldn't have been a better example of the polar vortex. But The main thing you want to take about here with the jet streams is they mark the barrier between the two different air masses. And that's the significance. The jet streams don't cause the thing, but they mark it. So what is a jet stream? Well, a jet stream is like a hose, like I said, very narrow. 1 to 3 miles is all it is, just a small thing, goes west to east. If you're flying in an airliner, they like to grab this thing about 7 miles up, and you'll add 200 miles. In Spanish, they say when you're flying from Spain to California, it's uphill. And it is really right, because you got to avoid the jet stream. Now, this is the polar jet stream, or any jet stream, and it's behaving itself. So it's up in Canada. And if it behaves itself, all this cold, icy air stays in Canada. What stays in, what's that saying? What happens in Las Vegas stays in Las Vegas. So this air is here making everybody cold and miserable, but we live down here in the temperate zone. So this jet stream marks the division between these two air masses. Once in a while, it doesn't behave itself, and we'll talk about why. What happens is then you get a tongue here pushing down on the jet stream. And this is called a trough of low pressure, a trough of low pressure. And over here, we have a ridge of high pressure. We'll talk about this a little bit later. This winter, we had a case where the polar vortex up here broke down. The job of the polar vortex is to keep the really cold polar air up in the polar region. And that's what it does. It corrals all that air up there and doesn't allow it to spread down south. But when the Arctic heats up, the polar vortex slows down. That also causes the polar jet stream here to slow down. And then when it slows down, it starts to undulate. That's exactly what happened this winter. So we had the polar vortex broke down, the cold polar air spilled into the United States. And so we had a trough of what we call low pressure right here. This is stormy air, low pressure. Over here on our west coast of the United States, we have a ridge of high pressure. So we had nice mild weather, hardly any rain at all, by the way. And over here, they got all kinds of stuff. Eventually, everything mellows out, the jet stream behaves itself again, and life is good. Here's a better example of what happened. So this is the polar air. Notice it's low pressure when it's coming down. That's associated with storms. And so here you've got your Arctic air, tongue of Arctic air, breaking loose from the polar vortex and coming down because it wants to go south. That's the polar cell air is coming south, and it's coming south big time. So it pushes right down into the east coast here. It says moderate cold. That's a joke. It was snowing in Atlanta. The East Coast just had snowstorm after snowstorm, sometimes record snow drifts, icy rain, horizontal rain, snow, thunderstorms, the whole 9 yards over on the East Coast. On the West Coast, the ridge of high pressure, the jet stream, that is the air masses, created very warm, mild conditions. This is very typical of a La Nina. If you remember when I gave the La Nina about half a year ago, I said this is exactly what's going to happen because we have a La Nina. And the La Nina causes this. And you could take a look in my talk on the La Nina and you'll see why all of this is going on. Unfortunately, this mild air also comes with a little asterisk. It reads drought. So whereas the East is literally flooding. I mean, there's disaster areas and floods declared over here. We have a disaster area coming, which is a drought. And that's the exact opposite. This is another kind of example. In the summer, the jet stream follows the sun north. And so it typically in the summer, it's mild and well behaved. So you normally don't see this bad stuff coming in the summer. In the winter, the jet stream follows the sun south. And this is when the polar air gets pulled down. And so this is where we get the same trough. Now I'm going to not quite tell the truth, but it's pretty good. Why does this mild trough occur here on the West Coast and not on the East Coast? And one of the answers is the gyre. The gyre moves in, and so now you have the circular high pressure air here. And so the jet stream and the air masses, the wall rides up over the top of the gyre and then falls down in here into this low pressure area. So that's one of the reasons. Another is the prevailing winds from the westerly, but that's not quite so important. That's not the whole truth, but it's a part of the truth. Again, this saves Palos Verdes. We don't get snow in Palos Verdes, whereas if we were over on this side, we would get snow. This area of the United States is called the paradise for weather. That is, if you like weather in all of its forms, this is where it happens, right here. I'm going to mention one thing very quickly. There's two cutting edge things on weather if you want to study it. The first one is that they've discovered that all of the currents in the ocean aren't separate currents. It's one continuous current all the way around the Earth. And up the most interesting part is that area in the North Atlantic gyre that I mentioned. This is where they're talking about, like, if we get too much global warming, we might get global cooling. That you might have heard that. Well, that would happen in Europe, not everywhere else, but certainly in Europe. So Copenhagen can turn into Moscow or Toronto, for example. The largest waterfall in the world is right here. There's more water going from the top of the ocean down to the bottom than there is in all of the waterfalls in all of the countries of all of the Earth. So this would make a super docent paper. A lot of stuff is going on, and cutting edge research is being done here. One other thing, there's giant rivers of moist air, the humidity, the water vapor air all over this area, and we don't know anything about them, but the satellites have finally picked it up. Like I said, humidity is invisible. You can't see it. You can't smell it, but you can feel it. You can feel this water saturated into the air. And it turns out that there's gigantic rivers of this saturated air blowing across the Earth. Again, bigger than any river in the world. And we sort of know where they are now, but if you ever want to do some research on this, this is where the rubber is hitting the road right now. Local weather, I've already bored everybody, half of you are asleep. So I'm going to do another one on our local weather. So if you want to know what causes inversion layers and Catalina eddies and June gloom and Santana winds and so on, I hope to have another video sometime. That's the end.
That was wonderful, Bob. Thank you.
And if there's questions, fire.
Bob, I
we
have a
do
question that I put in the chat for you about the ocean cleanup people.
Yes.
Do you know anything about them?
Yeah, there's a company, actually, some of the people on my dock volunteered for it. And he's designed kind of I want to call it a vacuum cleaner, but it's not, but that's a good analogy. And they went out to help with it. And it seemed to be successful. Unfortunately, the guys on my dock, their boat hit a storm and they broke some shrouds and had to come back. They didn't make it. The problem with it is it's not so much the garbage there. There might be a solution to that. The problem is that the sun breaks this stuff down into microparticles. And these microparticles never go away. They're going to be there forever. They just get smaller and smaller and smaller. And once you've got something the size of 10 atoms, there's no way you're going to be able to get it. But it's getting into the fish. The fish are eating it. And then we're eating the fish. And some of these microparticles now are so small that they can go through the blood-brain barrier in our bodies. And so they're thinking now this stuff might actually end up in the brain. And it's negatively charged. And so what happens is now you've got this brain, which we think is a whole big computer that runs on micro electric pulses, and you've got this negative charge coming into the brain. I mean, this is the blob that ate San Diego. We just don't know. And so basically everybody's tearing their hair out on this, and there is no solution that I know of. Any other questions?
There was one question we had, Bob, about the Pacific Gyre rotates clockwise.
Yes.
So the assumption is it stays in one place.
It pretty much does. However, it kind of follows the sun. So as the sun moves north in the summer, the gyre will also move north. And in the winter, it moves south. So if you're in a sailboat race, for example, you always want to check the local weather map and see where that hole is, which marks the center of the gyre. The interesting one is this Arctic gyre. Let's see if I can get back to it. It doesn't go north and south. Oh, I'm going the wrong way here. Wait a minute. Oh, well. Anyway, the Sargasso Sea moves east-west. And so in the summer, it's called the Bermuda High, and in the winter, it's called the Azores High. And we're not sure why it does that, but that's one of the major reasons for the hurricane season. Because especially in the Atlantic, the hurricane, the hot weather in the ocean lags the hot weather on land by about 2 months. And so the hurricane season, it should be in June and July, but it's actually in September and October. And that has to do with that gyre moving around.
Okay. One follow-up question. If the Pacific Gyre wind is coming from the southwest, does that mean it's picking up plastic trash from the southwest and bringing it northeasterly?
The Pacific Gyre wind is not coming from the southwest. The prevailing wind is coming from the southwest. So the wind should be coming from the southwest. The gyre is rotating. So in the North Pacific, it's going east. In our coast, it's going south. In the tropics, it's going west out towards Asia. And so it's called a vortex. Think of it as you pull the plug in your bathtub and you get this whirlpool. And so all of the trash is being driven into the center. And so the very center of this high pressure zone, that's where the garbage patch is. So it's not getting pushed out, it's getting pulled in. And I guess it's nice because all the crap is out in the middle of the ocean, but now we've created a monster.
Anne has her hand up.
I'm sorry, someone came in the room. What?
I just saw your hand up.
Oh, my hand up. Oh yeah, Bob. So what actually is happening besides microplastics is ocean cleanup still working? It can still get the big part of the big stuff, right?
In theory, yes. In practice, we haven't figured out how to do it yet. But this experiment that the guys on my dock were part of seems to work. And the idea is that they get a huge drift barrier like they do for oil spills, and let it drift with the gyre, and eventually it gets pulled in and kind of like corrals, like a purse net that catches the fish, and they can corral this stuff and take it away. But in practice, that's the theory. In the practice, nobody's been able to do it yet.
So as far as you know, it's still working.
Yeah.
Because they're not advertising, and they have a website and they're not updating their website.
Yeah, it's like I said, this is just theoretical.
Okay.
They've proven the concept, but this is going to be enormous expense.
Got it.
But and there's one in every ocean. So
And didn't they put one in some rivers?
I don't know about that.
Thank you.
And there were no other questions that came in on chat. If anyone has any additional questions, now's the time.
I'm gonna have to watch this at least 5 more times before it sinks in my head.
I have a question. This is Adela. Sometimes on the on the news, you'll hear that we have a low pressure that's stalled out. I think that's what they're saying. What does that mean? That it causes moisture not to come in and all kinds of things like that?
Yeah, that's called an occluded front. And what happens is a front is defined by, if the cold air is pushing, then it's called a cold front. If a warm air is pushing, it's called a warm front. It's the same front. It's just the direction that it's moving. Sometimes you get a Mexican standoff where neither one is moving, and that's where it's stalled. And it's a little bit complicated, but as it stalls, the front starts to rotate and create, I got right here, a low pressure. This is called what they call a cutoff low. And so the front breaks away and forms its own little low pressure cell. And that's what you're talking about there. That's the stalled low. And a lot of times this will collapse in on itself and cause thunderstorms, especially. This is one of the reasons that we have thunderstorms. It's part of a front that broke off and started spinning. But yeah, low pressures can stall, and it's usually caused by two different air masses pushing against each other. Usually the one right there between the polar air and the temperate air, the Ferrel cell. And there's a constant battle between these.
Okay, we have a question just in, Bob.
I have another question.
Go ahead.
What are they talking about? Sometimes pressure in that can keep the rain from coming to our area.
Yeah, that's that. Remember, I don't know how to get all these pictures here, but let me see if I can get that picture here. Yeah, here we go. See, this is where the gyre is coming. And so the cold rain wants to come, and Seattle just is above this. And so the rain comes in Seattle, and we're on the other side of this. So this is the polar air mass, and this is our temperate air mass. And this high pressure ridge is riding up over the gyre, again, clockwise. And so what happens is the rain is up here, but the high pressure where we have right down here, this is, remember, we live in a desert. Desert is caused by high pressure causes heat. And so the rain, instead of coming down to California, rides up over the gyre and comes down here and dumps all over the Southwest down here. This is good, but on the other hand, we're in a desert, and so we have drought. So the price we pay for that is that we don't get any rain. A lot of times in the summertime, late summer, this will drop down and as far down as Santa Barbara. So Santa Barbara can get a lot of rain that we don't get. And certainly Monterey and that area in San Francisco gets a lot of rain. So I think that's what you're talking about. And again, that's the stormy air riding up along the jet stream barrier here and up over the top of this ridge of high pressure. Yeah, did that answer the question kind of?
Yes, it did. Thank you.
And Bob, would you explain once again why they don't speak Spanish in Hawaii?
Okay, if I can find my gyre picture here, I can. Yeah, let's see. Uh-oh, yeah, there we go. Oops, going the wrong way. It has to do with the gyre. Remember I'm sorry, I'm not doing very well here. Oh, here we go, here's the gyre. There we go. So this is the center of the high pressure here again. And you can see Hawaii is right kind of halfway across the gyre. So if you're the first 4 Spanish expeditions tried to get back from Asia and sailed too low and went into the hole, and they all starved, and they ended up coming back starving to the Philippines and were captured by Portuguese battle squadrons. Remember, the Portuguese and the Spanish were duking it out really bad during the late 1500s, early 1600s. So the Spanish galleons that followed what they called the roundabout, La Volta, followed this circular path in the gyre, but they stayed away from the hole. And so that means that they didn't come up here where Hawaii is, because they were afraid they'd get stuck and then get starved. And so they stayed low. And because of that, they never went to Hawaii. It was only English people that were just wandering around looking for, exploring, and they found it. And so the Spanish never did land in Hawaii. They did land in Guam up here, but not Hawaii.
And Bob, can you explain what causes the eye of a hurricane or cyclone?
Yeah, remember in the cyclone, let's see if I can get the picture of the cyclone here really fast. I keep going the wrong way. I'm not used to these arrows here. I'm sorry, I'm not doing a good job here. There we go. Now I'm in the right area. Oh, there we go. Okay, this is a hurricane, which is a cyclone. The technical name is a cyclone. Hurricanes are cyclones. Cyclones are counterclockwise rotating winds around a low pressure. And if you pull the plug in your sink or your bathtub, you'll notice a whirlpool forms. The water is going down into the whirlpool, but it creates a little vacuum area in here that you could actually stick your finger in the middle of that hole and not be wet, because the centrifugal force of this spinning is pushing all this stuff out. There used to be a ride in Venice, in the old Venice Pike, and you'd stand there against a wall and they'd spin the wall around and then drop the floor, and you'd be pushed against the wall, even though you weren't standing on anything. Well, that's what's happening here. As the faster it is, the bigger the eye. And so this eye gets expanded out because of the rotational force. Same idea as if you take a rock on a string and start spinning it around, the rock's trying to go out. If it's a physicist on there, I apologize, because it's not quite that simple, but that's the idea, yeah.
I think that's all the questions for today.
Just to finish it up, again, the things that you can take away here are, we live in a desert. That's due to the descending air from the Hadley cells. The prevailing winds are from the southwest to the northeast, and that's because of the Coriolis effect. The gyres in the ocean provide this cool wind down the California coast that saves Palos Verdes from being like Bakersfield. And then the jet streams separate the air masses. And so we don't get the cold polar air coming down here and bugging us, because it can't, that polar air doesn't want to mix with the feral cell air. So if you've got that much out of it, we've been successful.
Thank you, Bob.
You're welcome.
Bob,
Yeah.